Hello, my name is Brian Corbridge, and I'm going to be discussing the uh, forces perpendicular and parallel with the world's largest swing. So, for a little bit of background, there's this guy, his name's Devin, and he decided to make a YouTube video where he makes the world's largest swing in Utah over this arch right here. So, he attaches a rope to right here, and then they jump off and swing through this arch. It's a pretty cool video. And yeah, we're going to be discussing the forces applicable to this scenario. So for starters, I was able to gather these screenshots from the video to give us a little more information on how we're starting and how we're going to set up our um, simulations. So here we can see that the rope itself is 150 feet, or it says in the next slide, but I believe that I did my calculations, it was around 47 meters, something like that. And so that's going to be the radius of our circle, of our pendulum. And then we can see from here that you're going to free fall 130 feet. This is important. You'll see in the next slide how I set up everything, because clearly they did not start at the same height as the um, point at which the rope is attached to the arch, because then they will have fallen 150 feet. But they only fell 130 feet, so we're going to see in the next slide how I set up the simulation. So we can see here, this is how I set up the situation just to make things a little bit easier. This point right here is where the rope is attached to the arch and where our pendulum is going to be swinging from. Here's the radius. I said 47 meters, I think, last slide. It's 45.72 meters, um, which is 150 feet, which is the length of the rope, which is this length here. And then I found that since we are our free fall, this length from here to the bottom of this circle is 130 feet. I did some trigonometry to find out that this angle theta is going to be 7.595 degrees, because we are not starting at the same elevation as the anchor point. And then as you can see here, here's a little bit of a free body diagram. So this is going to be the F net perpendicular, and this is going to be F parallel. Force tension, of course, is running F parallel. And then the force gravity is going to be a little bit different here. And again, this angle right here is going to be 7.595 degrees. For my calculations, I just made the mass 100 kilograms. It's a little bit heavier than the average person, but it just makes calculations a little bit easier. Um, as we go through, it just makes things a little bit easier to follow. So here are the equations I used to calculate the F net parallel and F net perpendicular. F net parallel, of course, we've been using this. This is nothing new. F net perpendicular, though, um, so it will be this is also equal to the force of tension plus mass times gravity times cosine theta, which is 7.9 or 7.595. But that all together is going to equal zero, because our velocity, since we're starting at rest, our velocity is zero. So F perpendicular is zero. And so here you're going to see me showing off my code I wrote for this simulation. As you can see, the theta, yeah, for theta I did 90 minus that 7.595 that we got earlier. And yeah, the string length is just going to be the radius, 150 feet. Like I said, we kept things simple by having the mass just be 100 kilograms, because we're just guessing it. That's not really too important. So here's the code I wrote. I got some bits from the black hole code, but most of it I just got for myself. And yeah, like as you can see, the F net perpendicular is zero, because I'm just finding it at the initial um at the initial time, and the velocity was zero. And that's what I got for F parallel. I did the calculations on my own, um, uh, over here on paper. And yeah, as you can see, here's that there's the little simulation I got.